Hi, I'm Dr. Christopher Sutton. Welcome to my Introduction to GIS video series. In the previous videos, we talked about geographic coordinate systems, latitude and longitude, and how they allow us to describe any location on Earth's surface. In this and the next two videos, we will cover projected coordinate systems, what they are, why we need them, and how they work. A projected coordinate system is a way of representing Earth's curved surface on a flat, two-dimensional plane, like a piece of paper or a computer screen. Instead of expressing locations using degrees of latitude and longitude, a projected coordinate system expresses locations using linear units, typically meters or feet, measured along a flat grid. You may have seen these grids before. Think about a standard paper map with a neat rectangular grid of lines running perfectly horizontal and perfectly vertical across the page. These lines define a projected coordinate system. Every location on that map can be described with an x-coordinate, called an easting, and a y-coordinate, called a northing. Together, those two values give you a precise, flat surface location for any point. Now, it's important to understand that a projected coordinate system is built on top of a geographic coordinate system. It does not replace a GCS. Before you can project Earth coordinates to a flat surface, you first have to define that surface using a geographic coordinate system and its underlying datum. In other words, a projected coordinate system is always based on a geographic coordinate system, but it adds a map projection to transform those angular coordinates into planar coordinates. Think of it this way. A GCS tells us where on Earth something is located. A PCS tells us how to represent that location on a flat map. So why do we need projected coordinate systems? Why not just work with latitude and longitude all the time? The answer comes down to one fundamental problem. You cannot flatten a sphere without distorting it. In previous videos, I discussed map projections, including how they are created and ways to minimize distortion. Recall that the projection process can introduce distortions, typically those of shape, area, distance, and direction. When you project Earth coordinates onto a flat plane, you will distort at least one of those properties, and often more than one. If projections always distort something, why do we use them at all? Because a flat map is enormously practical. Here's what working in a projected coordinate system gives you that working in geographic coordinates does not. First, distance calculations become straightforward. In a geographic coordinate system, the distance covered by 1 degree of longitude near the equator is approximately 111 kilometers. 1 degree of longitude near the poles covers almost nothing as meridians converge toward a single point. This makes measuring distances in degrees very complicated. In a projected coordinate system, the units are linear and consistent. A meter is a meter everywhere on the grid. Let's talk about how we calculate distance. On a flat plane, we use the Pythagorean theorem, which you may have learned about in a high school geometry course. The formula, you may recall, is a squared plus b squared equals c squared. The distance between 2 points, c, would equal the square root of a squared plus b squared. That formula is fairly straightforward. To calculate distance on a sphere using latitude and longitude, we need the Haversian formula, which involves sines, cosines, arctangents, and is significantly more complex than the Pythagorean theorem. If we want to calculate distances between 2 points on Earth's ellipsoidal shape, we use Vincente's formulae, which is even more computationally intensive. It involves multiple formulas, not just one. Beyond just computation, there is a practical reason for using projected coordinates. Most of our real-world features, property boundaries, road center lines, building footprints, forest parcels, and so on, are all defined using planar or Euclidean distances. Second, area calculations are reliable. If you need to know how many square kilometers fall within a polygon, working in a projected coordinate system gives you a trustworthy answer. Third, navigation and surveying become practical. A flat grid allows you to plot straight lines, measure angles, and calculate positions using simple plane geometry, rather than the much more complex mathematics of spherical trigonometry. Fourth is historical inertia. For centuries, surveyors have established networks of fixed monuments and measured distances from those points using Cartesian coordinates. That historical inertia still influences how we work today. Finally, for many everyday GIS distance operations such as overlay analysis, buffer creation, and proximity calculations, your software is using two-dimensional geometry. If your data is in geographic coordinates, those calculations are either approximated or require the software to do additional work behind the scenes. Working in a projected coordinate system allows mathematical operations to be straightforward and easy to calculate. In upcoming videos, we will dive into two of the most important projected coordinate systems you can use as a GIS practitioner in the United States: the Universal Transverse Mercator System and the State Plane Coordinate System.